Good morning. The video I want to do now, it's something a little different. It's not going to be one of my usual astrology videos. It's not going to be one of my music videos where I'm playing guitar rather badly. And it's not going to be one of my videos on rabbinic literature or Jewish mysticism. Instead, this video is for those who want to learn something about group theory, the mathematical theory of groups. And I'm basically just going to introduce you to materials I have on my web page, which give you a new way to learn about the theory of groups. So let's see if I can share my screen here. Okay. Let's see, I just need to get one or two things out of the way. All right, so this is where you would want to go. This web page is www.docbenton, DOCBENTON.com, and it's called Doc Benton's Academy for Mathematical, Astrological, and Kabbalistic Wizards. And near the top here, I have what I call a child's garden of groups. And this is 900 plus pages of an introduction to the mathematical theory of groups. And it's organized very differently from the way most group theory courses are organized. All the materials here are free. Uh, are there typos in what I have? Of course there are. There are places where I say that 2 plus 2 equal 5 or worse. But as I say, I'm old, so find and fix the typos yourself. Now I've got 10 modules here. And one of the things which is different is I don't even begin to start proving theorems until module 9. And in this module, I give proofs for a lot of theorems. All the proofs, though, are fairly short and fairly easy. Most group theory courses, they kind of begin here, proving theorems about group theory as soon as you give the definition. And then the very last module is titled Isomorphisms, Homomorphisms, and Theorems. Oh my. And this gets into deeper theorems involving group theory, and the proofs are longer and more complex. But we start here with an introduction to the mathematical theory of groups for young and old. And I just want to walk you through the table of contents of each of these modules to give you an idea of how it's laid out. And a lot of the material here is accessible to anyone who's had just a basic course in algebra and was good at it. So that means that most of the material here is accessible to not only students in high school, but some students in junior high, as long as they've had a little bit of algebra and are good at and enjoy mathematics. So let's look at the contents for this first one. And it begins with what is a group, examples of group, clock arithmetic, cyclic groups, symmetry, multiplication tables, permutations, multiplying permutations, permutation groups, group actions, Rubik's Cube, installing GAP software. GAP is it's freeware you can download online. GAP stands for Groups, Algorithms, and Programming. Then how to use GAP Part 1. Every module has something on GAP. And then we have something from something creation. You're not going to find that in any group theory books. I think in the second module, I talk about something from nothing creation. And so this is something you might find interesting, which is quite new. Then I have a summary, practice problems and practice problems with answers, and hopefully my solutions are correct. And at the very end, there's always I believe, a cool picture. Oops. There we go. It takes a while for technology to catch up with what I'm doing. So, study group theory, be a god. And there we have Odin with his one of his ravens. Okay. This is sort of the picture at the beginning of each of these modules. Now, one thing that's interesting about this, or one thing I put an emphasis on, is that uh, groups are basically built up from cycles, putting cycles together. So I get into cycles and cyclic groups early on. Groups also involve symmetry. You could say, just as numbers sort of measure how big or how small something is, mathematical groups measure how much symmetry something has. I get into permutations as a natural way of talking about groups. And I show how to multiply permutations, a couple of different ways, get into permutation groups. And early on, I introduced the notion of group actions. In other words, what that is you have some set of objects, and then you have a permutation group that consists of permutations of those objects. So every element of your group is a permutation of these objects, so the group acts upon those objects. Now, as a natural way of sort of understanding group theory, and experiencing groups hand-on, I talk about Rubik's Cube. And I pretty much reference Rubik's Cube throughout. And in every one of these modules, I show you how to do things in GAP software. This software is another way to get sort of a hands-on experience of groups. And because I want this to sort of feel real and hands-on, most of what I do throughout deals with what we think of as groups of small order, things which are small enough for you to analyze and get an understanding of. So another way to say this is I focus more on finite groups, groups with a finite number of elements, than on infinite groups, things with an infinite number of elements like the real numbers or the rationals or the irrationals or even the complex numbers. Okay, now let's see if I can go on to the second one. Even though I don't do proofs until much later on, there are some topics that I introduce very early. So in the second module, I get into subgroups, right cosets, left cosets, quotient groups, which are very important, equivalence relations, which are very important, something from nothing creation. This has to do with quotient groups. And I don't know if any of the people in artificial intelligence are working on trying to create human-like robots or androids or whatever realize this at this point. I don't know if anyone besides me realizes it, but uh, quotient groups are a way in which we change the structure of something by literally putting two and two together. Two become one to create something new in essence. And this is how we as human beings engage in something from nothing creation. When the two become one, that's like a big aha moment, which just bursts onto the scene out of nowhere. So it's like something from nothing creation. And it's what humans do all the time. And if some sort of computer simulation needs to pass itself off as a realistic human, it has to be able to create quotient groups in its mind. It has to be able to combine elements together to create something new. Then I talk about certain special subgroups. I think that's things like the center of a group, commutator subgroups, and others, normal subgroups. And then I get into exploring Rubik's Cube with GAP and have another tutorial on GAP in which I show you how to do more things with that software. Okay, moving on to the third one. This gets into some very special kinds of groups. Cyclic groups, dihedral groups, symmetric groups, alternating groups, direct products, semi-direct products, the quaternion group, generators for a group. And then we have another GAP tutorial, groups, algorithms, and programming, summary, and more practice. And so these are going to be some of the main different kinds of groups you want to be aware of and be able to construct or identify. At the very end, let's see, I probably have another picture. Oh, yes. The S here, of course. It stands for Symmetric Group Man, the man of groups, able to form quotient groups in a single bound. Well, let's go back up here. And let's see, take a look at part 4. Part 4, I just do a thorough analysis of the structure of groups of order 1 through 10. So the order of a group is the number of elements in the group. So some orders have just one group. There's only one group of order 5, which is a cyclic group. Other groups like groups of order 8, they're going to be several. So I can show you exactly how many groups there are of each order. And let's see, we take a bit of a dive into their structure. Let's see what I have here. This is the direct product of the cyclic group of order 2 with another cyclic group of order 2 with another one. That's going to give us a group of order 8. It shows us using what we call cycle notation. Generators. Everything is done in cycle notation, which is a way of showing permutations. Because if you know the elements which are being permuted, and if you know the permutations which generate the entire group, you can actually create the whole thing from scratch. You can figure out the multiplication quite easily. So we answer questions like, is a Abelian or commutative group? We show the basic subgroups, normal, center, CLO2 subgroup. That's all explained earlier. And normal commutator subgroup. And let's see, what else do we have here? Oh, we have what we call a subgroup lattice, which shows the main group, all the different subgroups of it, down to the identity element. Okay, so that shows you a lot of structure of groups that are small enough to really get into that structure. And you can thoroughly analyze the structure of groups of order 1 through 10, see how many groups there are of each order, etc. Then the next module is on visual representations of groups. Again, we do this for groups 1 through 10, and I present basically about 3 different ways of representing a group visually. We have what we call cycle graphs or diagrams, Cayley graphs or diagrams, and then something I came up with, though I doubt that I'm the first one to come up with it, it's what I call generator diagrams. And of course, I show more on how to use GAP software, and also visually how to find the quotient of a Cayley diagram. Well, that'll make more sense if you read parts 1 through 5. Okay, parts 1 through 4, rather. Next module is all about symmetry and ways in which groups are represented by symmetry, for instance, in art. I explain frieze groups. Those are those decorative patterns you have going around uh, the top of some of those Greek columns, wallpaper groups, and then something a little less rigid than frieze groups or wallpaper groups in terms of the rules, something I call free range symmetry, which relates more to how we identify certain kinds of symmetry in our lives, and both visually and otherwise. And you just sort of focus on that symmetry and ignore the rest of what's out there. And then I get into more lessons on GAP software. Now, in all this stuff on symmetry, let me go down a bit. Let's see what we got here. Oh, okay. I have some flow charts which show you how to identify the group um, related to a particular kind of symmetry in a frieze group. And then I do the same later on for wallpaper groups. There we go. I've got a flow chart which helps you identify uh, the particular group related to a symmetrical pattern that you see repeated in a wallpaper design. And all of these, I give several examples that follow and just kind of go over these things in detail. So this is kind of a fun thing to do. Okay, let me get back to the top here. So that's part 6. Part 7 gets into matrix groups. This is our late dog, Cleo, with glasses on. She's actually reading a calculus book here. As I say, group theory really is for everyone. So pretend this is a group theory book. Let me go back up to the contents for this one. I get into what is a matrix? It's a rectangular array of numbers, but certain matrices can go together using regular matrix multiplication, usually to form groups. So I talk about permutation matrices, other kinds of matrix groups, and also more on how to use GAP software. Let's see if I can get into some of the other matrix groups here. Okay. Permutation matrices. Here we go. Other matrix groups. I talk about the general linear group of degree n with real number entries, invertible upper triangular matrices, invertible lower triangular matrices, reflection matrices. Matrices can be used to create reflections about your vertical or horizontal axis. Invertible diagonal matrices. A diagonal matrix, it has numbers down diagonal from upper left to lower right, zeros everywhere else. Invertible scalar matrices. These matrices can make something look a lot bigger or smaller by multiplying by the right thing. Sort of like Ant-Man here. Rotation matrices. Orthogonal matrices. Okay. Let's see if I have some others here. And that's the end of those other kinds of matrix groups that I cover. Oh, then we take a deep dive inside Rubik's Cube, talking about conjugates, commutators, centers, and orbits, how to find those things on Rubik's Cube, how to count the number of permutations in Rubik's Cube, uh, various nice little patterns you can find on Rubik's Cube, how to create them, and a little revisiting of the solution to Rubik's Cube, and of course, how to use GAP, Part 8, and Rubik's Cube subgroups. So this really ties in Rubik's Cube with group theory. And finally, I get into proving some theorems here. And I have first an introduction to symbolic logic, a few pages of that. And then I have some standard theorems which are pretty easy to prove. Things like the identity element in a group is unique. If you have a group, if you have something like A times B equal to A times C, I prove that you can cancel out that A to show that B is equal to C. Okay, where these are all elements within a group. I show that inverse elements and groups are unique, and just lots of other basic theorems, which are pretty simple and pretty easy to prove. Covers a whole bunch of stuff. And let's see. Let me go back up a little bit. And then the very last one, isomorphisms, homomorphisms, and theorems. Oh my. Here's where I get into some of the deeper theorems of group theory. Most books on group theory will have proofs for the majority of these theorems. Others are even more advanced and may not have complete proofs. I just hope all my proofs are correct. But like I say, I make typos. I'm old. You correct them. You find them. So I define functions, isomorphisms, and homomorphisms, homomorphisms and identities, homomorphisms and inverses, the kernel of a homomorphism, the natural homomorphism, correspondence theorem, homomorphisms, and one-to-one functions. Okay, our three basic isomorphism theorems, known as the first isomorphism theorem, the second isomorphism theorem, the third isomorphism theorem. Some applications of that. I talk about quotients of quotients of quotients. A lot of this stuff I wrote some years ago so that I could reread it when I get old and forget. So I think that time is about here for me. uh, then orbit stabilizers, fixers, and Burnside's counting theorem. That's not always contained in basic books on group theory. I explain mathematical induction. A lot of theorems about and results about conjugates in groups. So I call this conjugal math. And then I talk about the CELO theorems and give proofs for them. And I end with a proof of the fundamental theorem of abelian groups. And then, of course, there's also uh, another tutorial on GAP, how to use GAP, part 10, summary of the whole thing, practice problems, and practice problems with the answers. And at the very end, let's see, another cool picture. The group theory is strong in you. If you make it this far, I can guarantee you will be strong in group theory. Okay, let me go past my Alice in Wonderland picture. Back to the contents, and I'll leave that. And that is the end. So let me stop sharing my screen. Let's see, I gotta shift some things here real quickly. Okay, and I'm back. So if you're a mathematics major, if you're interested in group theory, if you just want to learn a little bit, you can read the first module or two. As long as you know something about algebra, you can learn just from the very first one how group theory has to do with both cycles and permutations and symmetry. Uh, and if you're more advanced, you can go further on. If you're really intent on learning group theory and learning theorems and proofs, well, this can really, I think, give you a good solid foundation in your group theory. Show you how it relates to Rubik's Cube, show you how to use GAP software to explore and understand group theory further. And like I say, this is organized very, very differently from most books on group theory. But I think it's a better organization, a better way to get into it. And it's tailored, so if you just want to know a little bit about it, just do one or two modules. If you're a mathematician, you want to know a lot more about it, just go through the whole thing and correct all my typos and errors as you do so. Okay, well, that's it. I hope you enjoyed group theory. I hope you enjoyed this introduction. And we'll see how many people find this video on the internet. And so for now, I'll just say so long and be well.